Hello students, today we are going to discuss about limits involving exponential and logarithmic functions. This is a topic in your supplementary material of class +1 exercise 13.2, which involves the use of two formulae, that is limit x approaches to 0 e raised to power x minus 1 upon x, that is 1, and limit x approaches to 0 log of 1 plus x upon x is equal to 1. Now see what is the definition of exponential function. The exponential function f with the base b is defined as fx is equal to b raised to power x, or we can call it as y is equal to b raised to power x, where b is a positive constant other than x and is always a real number, right? So what is that? Exponential function f with a base b, it is defined as fx is equal to b raised to power x, or we can write it as y is equal to b raised to power x, where b is some positive constant and x is any real number, right? Now some examples of exponential functions are there, like fx is equal to 2 raised to power x. Now here what is the base? As here the base was b, the base here is 2. Similarly gx is equal to 10 raised to power x, so the base here is 10, and hx is equal to 3 raised to power x plus 1, base here is 3. What are logarithmic functions? The inverse of exponential function is the logarithmic function. So remember, the inverse of exponential function is logarithmic function. Like for x greater than 0, a greater than 0 and a not equal to 1, if a raised to power y is equal to x, if a raised to power y is equal to x, then we say or define the logarithmic function y, see from where this y is coming, y as log to the base a, log to the base a of x. Okay, so that means if y is equal to log to the base a raised of x, then we say x is equal to a raised to power y. And here this function fx is equal to log to the base a of x is called as logarithmic function with base a. Okay, so say for example, we are familiar with that 10 raised to power 0 is equal to 1. Okay, 10 raised to power 0 is 1. Now look here, just comparison. What is there in place of a? It is 10. What is there in place of y? It is 0. And what is in place of x is 1. So if I need to write it back in the log form, how will I write? I will write it as y is equal to log to the base a of x. Okay, so who is y? 0, and log to the base a. Who is a here? To the base 10 of what? X, 1. Okay, so that simply means log of 1 is 0, to the base 10 is 0. So this is how we define our logarithmic function. Now the difference between means what we call as your e raised to power x function, and one is your y is equal to 2 raised to power x. When we defined our exponential function, we found that some number was raised to the power of x. Okay, so like here 2 raised to power x, we took in example 2 raised to power x, 3 raised to power x. Okay, so if the functions like 2 raised to power x, okay, whenever your number here is a real number, okay, any positive real number, so in that case it is called as your common exponential function. It is called as common exponential function. And when in place of any other real number, a fixed number e is there, we call it as natural exponential function. We call it as natural exponential function. Okay, so this is the basic difference between, see, y equal to 3 raised to power is a common exponential function. Y is equal to 2 raised to power x is a common exponential function. But y is equal to e raised to power x is a natural exponential function. Okay, so what is e here? What is e here? We are writing here as e. So what is e here? E is a number whose values lie between 2 and 3 and its value is approximately 2.71828. Okay, and these are the graphs of, you know how to plot the graph of 3 raised to power x. Try different values of x, so it will be 3 raised to power 1, 3 raised to power 2, 3 raised to power 3, similarly 3 raised to power -1. So you will obtain this darker green one is the graph of your 3 raised to power x. Okay, and y is equal to ex, the graph 2.7 raised to power 1, 2.7 raised to power, so blue one is depicting the graph of e raised to power x, and y equal to 2 raised to power x, that is again your 2 raised to power 1, 2 raised to power 2, and or 2 raised to power -1. So this light green color is depicting the graph of 2 raised to power x. And can you observe one common thing? All of these graphs are passing through a point that is 0 and 1. Okay, and similarly here are what we can observe here is, like if we need to plot for 2 raised to power -1, so it can be plotted as 1 by 2. Okay, for 2 minus 2 it can be plotted as 1 by 4, 2 raised to power -3 as 1 by 8, and similarly 2 raised to power -4 as 1 by 6. Now these are the graphs of comparison of graph of logarithmic and exponential function. So see, this your graph of 2 raised to power x. Okay, so we plotted right now the graph of 2 raised to power x. Okay, the graph of y is equal to log to the base 3 of x. So by the definition of this logarithmic function, what will be there? It will be your this x will be equal to 3 raised to power y. Okay, and similarly y is equal to log to the base of x, so x will be 2 raised to power y, and y is equal to 3 raised to power x. Okay, so the comparison shows, as we have recently plotted the graph of our what has happened here, y is equal to 2 raised to power x, and here x is expressed as the 3 raised to power y. Okay, so similarly what is the difference between these all functions? And that is, in both these functions the expression is in the form of y is equal to 2 raised to power x or a raised to power x, and in both of them your x is expressed as your a raised to power y. Okay, so both of them are inverse functions of each other, right? Inverse, which can be clearly observed from the graphs also. So you know that the exponential functions y equal to 2 raised to power x and 3 raised to power x will be having these kind of graphs. Okay, and this x equal to 3 raised to power 5 and x raised to power 2 raised to power y will be having these kinds of graphs. Okay, so what are the properties of exponential and logarithmic functions? Exponential function, a raised to power x and or e raised to power x, the natural one. Okay, where a is any real number, positive real number, and fx is log to the base a of x. The domain of the function of this exponential function, the domain is set of all real numbers, means you can put anything, you will always get a value for your e raised to power x, like e raised to power say 1 is e raised to power square is as your e square. Okay, or if I put the value as 2.7 square, so you will definitely get a value. Even in cases of e raised to power -1, it will be something like, which will always be a output is always coming out to be a positive real number. Okay, so that's why the range of this function is your 0 to infinity. Okay, now since your log is a function which is inverse of your exponential function, so domain here, the domain changes to range and range changes to domain, right? So domain of this function is what the range of exponential function was, that is 0 to infinity, and range is your what the domain of exponential function was, -infinity to infinity. And definitely as we observed in the graph that it is touching y-axis at 1 and this will touch x-axis at 1, and it has no x-intercept, means it is 0, and here the y-intercept is 0. Okay, so we observe that the graph of this is passing through the point 0, 1, and the graph of this will pass through the point 1, 0. Okay, now here in our this topic we are going to study about limits of logarithmic and exponential functions. Okay, so the very first result is very simple, limit x approaches to 0 e raised to power x. So you know we can directly put the limit as e raised to power 0 and the answer will be 1. Anything raised to power 0 is 1. And we need to observe about now these two formulae, that is we need to derive about this formulae how this result will come as e raised to power x minus 1 upon x is 1 and log of 1 plus x upon x is equal to 1. So let us derive the first formula, that is prove that limit x approaches to 0 e raised to power x minus 1 upon x is equal to 1. Okay, so in order to prove this theorem we need to use an inequality. Okay, so we need to use an inequality, that is, what is that inequality? Is 1 upon 1 plus mod x less than equal to e raised to power x minus 1 upon x less than equal to, it is 1 plus mod of x times e minus 2. Okay, so this is the inequality which we will be using to prove this above limit. Okay, and the important condition here is that x belongs to your closed interval minus 1 to 1 except 0. Why 0? Because we need to leave 0, otherwise this result does not hold. Okay, it does not exist, right? With the help of this inequality we will be proving this result. Now how this result will be used, as you people are aware with sandwich rule, and sandwich rule was having it was all about your three functions where say a function fx is lying between your gx and hx. Okay, and the limit of means say gx is giving you some value, hx is giving you some value. Okay, so the function that is lying in between fx, that is fx like function which is existing in between these two functions, will also take that value of the limit. Okay, so we will be using that result to prove this. So let us see how to prove it. Okay, so using this inequality, what is going to happen? Say I'm taking my left hand limit. Okay, so towards my left hand side, what is there? Limit x approaches to 0, your 1 upon 1 plus mod x. So as it is a simple function, it is not framing any form, so I can directly put the limit. So it will be something like x approaches to 0 mod of x, which is 1 upon 1 plus 0, that is 1. Okay, similarly to the right hand side, limit x approaches to 0, it is 1 plus mod x e minus 2. Now here also, and there is no problem in substituting the limit directly here, so it becomes 1 plus 0 times e minus 2. That makes this complete term as 0 and it reduces to 1. Now what happens according to the sandwich rule? Okay, so therefore by sandwich rule, what is happening? The limit of gx is 1, limit of hx is 1. So what will happen? That the limit x approaches to 0 of this fx, who is fx? E raised to power x minus 1 upon x, this also reduces to 1. So this is the proof of this theorem, that limit x approaches to 0, ex minus 1 upon x is equal to 1. This result is your logarithmic one. So our next theorem is to prove that limit x approaches to 0, log of 1 plus x upon x is equal to 1. Here the base here is the natural one, that is log to the base of e. And for proving this result, we will be using the result that we have done, that is your limit. We will use this limit x approaches to 0, ex minus 1 upon x, that is equal to 1. Okay, so how to prove it? Let us see. Firstly, I will put this result, whatever I am desiring to prove, as y. 1 plus x upon x is equal to y. So this will imply log to the base e of 1 plus x is equal to xy. Okay, this is equal to xy, right? Now the property of log, what does it says? A raised to power x is equal to b. That means log to the base of a of b is equal to x. Okay, so in that way, let us see log to the base of e of 1 plus x is equal to your xy. So how will it happen? It means that e raised to power that xy is equal to 1 plus x, isn't it? So it will reduce like this. Now let's bring this 1 to this side. It is e raised to power xy minus 1 is equal to x. Now divide by this x. Okay, so it will become e raised to power xy minus 1 upon x is equal to 1. Why 1? Because x has been shifted to the denominator. So again, if I cross multiply, it will again come here as e raised to power. It means it makes the previous result. E raised to power xy minus 1 upon x is equal to 1, right? So again, I know if I need to use this formula in place of, as the power is e raised to power xy, I need xy here also. Okay, so for it, what I need to do, I will multiply and divide by y. Okay, I will multiply and divide by y towards the left hand side. What I did, multiply and divide by y in left hand side. Okay, now take limit. Taking limit, I will take the limit. Okay, now if x is approaching to 0, what will happen to xy? It will also approach to 0. So this thing implies limit xy approaches to 0 of e raised to power xy minus 1 upon xy, okay, and into y. This is equal to, now limit is not applied to this one as it is constant, so it will be 1 itself. Okay, so you can write it as limit xy approaches to 0 e raised to power xy minus 1 upon xy, okay, into limit x approaches to 0 your of y. This is equal to 1. Now this result, by using 1, reduces to 1. So it is your 1, and I get the rest of the thing as limit x approaches to 0 of y is equal to 1. Okay, now who is y? Y is your this what we substituted. So I get it as limit x approaches to 0, limit x approaches to 0 of log to the base e 1 plus x upon x, that is equal to 1. Okay, so this is our desired result. Let us start solving exercise 13 point. Okay, so exercise 13.2, the first question is evaluate limit x approaches to 0 e raised to power 4x minus 1 upon x. So by looking at it, I can see that here I can use limit x approaches to 0 ex minus 1 upon x, which is equal to 1. Okay, but the difference is that in place of x, I need x here. So in place of 4x, I need 4x here. So how can I get it? Limit x approaches to 0 e raised to power 4x minus 1 and divide and multiply by 4. Now as x approaches to 0, 4x also approaches to 0. So here I can write it as 4x approaches to 0. By above result, this reduces to 1. So 1 into 4, and the answer is 4. Question number 2. Question number 2 is limit x approaches to 0 e raised to power 2 plus x minus e square upon x. So to solve it, firstly I need to split this term e raised to power 2 plus x. Okay, so can I write it as e raised to power square into e raised to power x? Yes, bases are same, powers are added. So limit approaches to 0, and what I can take common here is e square. Okay, and it is e raised to power x minus 1 upon x. So e square is free of limit, can be taken outside, and I get the direct result here as limit x approaches to 0 ex minus 1 upon x, that is 1. Okay, so it is your e square into 1, and the answer is e square. Now question number 3 is, it is your limit x approaches to 5 e raised to power x minus e raised to power 5 upon x minus 5. Now see, the result is regarding limit x approaches to 0. Here x is not approaching to 0, but I can make it to approach 0. How? Put x as 5 plus h. As x approaches to 5, h will approach to 0. So it becomes limit h approaches to 0, e raised to power 5 plus h minus e raised to power 5. And it is 5 plus h minus 5. So if you observe it, now it has become same as your question number 2. So it is again split e raised to power 5 into e raised to power h minus e raised to power 5 upon h. So again I can take this e raised to power 5 common outside, limit h approaches to 0, eh minus 1 upon h, which by the same result, limit x approaches to 0, ex minus 1 upon x as 1 can be reduced to e raised to power 5 into 1, and the answer is e raised to power 5. Question number 4. Number 4 is limit x approaches to 0, e raised to power sine x minus 1 upon x. Okay. Now see here, in place of x, here is sine x. So definitely in the denominator also I need sine x. So what will I do? I have to express it in standard form. So here sine x is there. So I will divide and multiply by sine x. And this x which was previously there, I don't need it with e raised to power x minus 1. Okay. So I will adjust it with the other sign which I used for multiplying. Okay. Now how the limit will be adjusted? As x approaches to 0, and you know sine of 0 is 0, so sine x also approaches to 0. So I will just write all of them in standard form. So here it will be sine x approaches to 0, e raised to power sine x minus 1 upon sine x, and here it is simple limit x approaches to 0, sine x upon x. Okay, so this result reduces to 1, this also reduces to 1. Okay, and the answer is 1 into 1, that is 1. Question number 5. Question number 5 is limit x approaches to 3, e raised to power x minus e cube upon x minus 3. Okay, so again you can see what we need to do. Limit is not approaching to 0. So put x as 3 plus h. As x approaches to 3, h will approach to 0. So it is limit h approaches to 0, e raised to power 3 plus h minus e cube upon 3 plus h minus your 3. Instead of h, it is 3. So it is 3. So it's changed. So it is limit h approaches to 0. Now you know what we need to do is e3 into eh minus e cube upon h. Take this e cube common outside. Limit h approaches to 0, eh minus 1 upon h, which reduces to 1. And the answer is e cube into 1, that is e cube. Okay. So question number 6 here is limit x approaches to 0, x ex minus 1 upon 1 minus cos x. Now see here, this ex minus 1 requires x in the denominator. So firstly I'll do some adjustments. Okay, So it needs x, give it a x in the denominator and multiply by the same. Earlier one more x was present here, okay, and you were having 1 minus cos x. So I cannot still, because this will become 1, that is okay, but I cannot apply the limit 0 directly here. Why? Because it will be 0 by, and 1 minus cos 0 is 1, so 1 minus 1 is 0, 0 by 0 form. Okay, so I need to search out for something that I can change to. Okay, so 1 minus cos x, you very well know, is 2 sine square x by 2. Okay, so I'll change it like this. Limit x approaches to 0, e raised to power x minus 1 upon x into, it is your x square, and it is 2 sine square x by 2. Okay, so see, now it is not affecting, so I will just separate it, means I can just separately write as your e raised to power x minus 1 upon x. Okay, so this limit can be given to it into limit x approaches to 0. See what is happening. Your 1 by 2, this 2 can be taken outside, so it is 1 by 2. Okay, so it is like sine square x by 2 can be written as sine x by 2 whole square. So it need x by 2 with it. Okay, then only it will be your sine x upon x form, and 1x square is, it was already lying there. Okay, so what is happening? This is 1 by 2. This result is your 1 into your this c x square, and from the bottom you will get, because this result will be just sine x upon x, but this is some extra thing with you, so it is x square by 4 in the denominator, which will come out as 4 upon x square. So this gets cancelled, and you can simply write it as limit as x approaches to 0, so x by 2 also approaches to 0. So in the denominator it will be something like this, sine x by 2 upon x by 2 ka whole square. Okay, so it is again 1 square, so that means this result is 1 by 2 into 4, that is 2. See the use of other formula, that is your limit x approaches to 0 log 1 plus x upon x, and the next question number 7 is based upon use of this formula, and the question is limit x approaches to 0 log to the base e of 1 plus 2x upon x. Okay, so clearly it is visible, the formula which we are talking about is limit x approaches to 0 log of 1 plus x upon x is 1. Okay, so here it is x, you need x, so here it is 2x, you need 2x here. So what would I need to do? I will multiply and divide by 2. Why? Because x is already there, so just 2. Okay, so as x approaches to 0, shall I say 2x approaches to 0? Yes, so the constant 2 can be taken outside, and it is limit 2x approaches to 0 log to the base e 1 plus 2x upon 2x. Okay, that is your 1 by this formula. So it is 2 into 1, that is 2. Okay, now let us see our last question, that is number 8. Limit x approaches to 0 log of 1 plus x cube upon sine cubics. Okay, now see from here that you can see two results. One is log 1 plus x and one is sine x. And you know sine x needs x here in the denominator, and this also needs some x, whatever x is required. Like here x cube is required, and for sine x also x cube is required. So I will apply the limits to numerator and denominator separately, and it can be written as 1 plus x cube multiply and divide by x cube. So there is no need to multiply and divide. Why? Because this x cube is adjusted here as sine x whole cube, okay, upon x. So see from here, it is actually sine cube x upon x cube. So I have multiplied and divided both numerator and denominator by x cube. So it is adjusted here. Okay. Now there is one thing which I need to amend is 1x approaches to 0. So x cube approaches to 0. Okay. So here I can, you must represent it in proper form. Okay. before applying the limit. 1 plus x cube upon x cube, right? And the denominator is just limit x approaches to 0. So you can view it as this one, or it is okay like sine x upon x whole cube. Okay, so the two result that we are using is limit x approaches to 0, sine x upon x is 1, and limit x approaches to 0, log of 1 plus x upon x is 1. So it becomes your 1 upon 1, and the answer is 1. So I hope the concept of how to apply both these results is clear to you, and it will be easier for you now to solve the exercises. Thank you.